Hey guys, this is video number 2 for chapter 20. Um, I am going to be talking about a lot of things off the cuff, as I kind of did in chapter 1. Not all of it is in the chapter, as I did in chapter 1, as I did in video 1. Not all of it's in the chapter, so I really would advise you taking notes because you may use any of your notes for the test, and so make sure you take notes. All right, so let me recap a couple things from last time we talked about atomic structure. You have to remember what atomic structure is from chemistry. That is that in the nucleus there are protons, positively charged protons, neutrally charged neutrons, and around it are electrons, negatively charged electrons. These electrons are what flow for electricity, and it's just the outer layer of electrons that can be ripped off. They're called free electrons. They're the valence electrons in there, and they can move around and be distributed. When it gets distributed to something, when the electrons leave something, that thing becomes more positive, and when they go to something, that thing becomes more negative. When you gain electrons, you become more negative. When you lose electrons, you become more positive. And let's talk about I talked about conductors and insulators last time. Conductors are things that these electrons can move through fairly easily. The more easy it is for something to move through it, the better conductor it is. The more difficult it is to move through, the more of an insulator it is. Insulators doesn't mean it can't move through. It's just more difficult. And what makes something a conductor or an insulator is just its microscopic structure. So the first thing I want you to look at is on page 546. There are 4 characteristics that you need to know. 4 characteristics of charges. First, that charges can be positive or negative. Charges can be positive or negative. One of the things I'm going to do a lot in this chapter is contrast charge with gravity, because force of electric charge, electric force, has a lot to do with has a lot of similarities, but also some differences. That's one of the big differences. Is gravity cannot be negative. It's just always an attractive force. But the electric force, their forces on charged bodies, these electric charges can be positive or negative. Okay, which means they can attract or they can repel. So it's the first thing. They can be positive or negative. Next, charges exert forces on other charges at a distance. Okay, it's a field. In other words, it's a field force. Just like gravity is a field force, charge is a field force. It can may exert a force over a certain distance. It does not need to be touching. But like gravity, the farther away you get, the weaker it is. Oh, that's the third one. The forces are stronger when the charges are close together. That means they're weaker when they're far apart. So, that's pretty typical. And the fourth part, like charges repel, opposite charges attract. That means a positive is going to attract negative, but if you're positive and positive, they separate. It works like that with magnets too. If you've ever put a magnet and they stick together, and you flip one over, you can't get them to stick together, right? And so that is those are the 4 characteristics of charges. I want you to understand that there's conservation of charge. You don't have, when you have like 2 objects. Whenever we hear conservation of something, okay, what it means is that something can't be created nor destroyed. You can't just lose it. Okay, like conservation of mass. Mass is how much matter is in an object. It says matter cannot be created nor destroyed in a closed system. In a closed system, if matter is lost from something, it has to go somewhere. It has to be added somewhere else. Okay? As long as it's a closed, isolated system. And we're assuming it is. In here, whatever we're talking about as a closed, isolated system, if something loses electrons, those electrons go to that other thing. I talked about in the video a glass rod being rubbed with a piece of wool. If those charges leave that glass rod and go to that they have to go to that piece of wool if we consider them a closed, isolated environment. conservation of charge. There's conservation of blank, and they just mean that it can't be created nor destroyed. When charges leave one thing, they have to go to that other thing. Um, Let me talk about polarization. I talked about this a little bit last time. I didn't tell you what it was, but you can charge things in two different ways. When you, like we talked about rubbing some pole with some glass pole with a piece of wool, and now let's say that glass pole is negatively charged, okay, because it gained, actually it should be positively charged. Let's say that pole is positively charged, okay. I have a positively charged pole. What that means is that some electrons have left. I'm going to draw this pole here. Okay, so I have a pole, and it still has some negatives in it. See, it still has some negatives in it, but it's mostly positive. So this would be considered a positively charged rod because it has an excess of positives. Well, what happens is, let's say I bring a neutrally charged rod in its place, and this rod normally would look like this, let's say. I'm just going to really simplify it. It's neutral, right? Well, what happens is, because we know that like charges repel and opposite charges attract, since there are positives here, okay, what will happen on this neutral rod is all of the positives will go to one side. Okay, all the positives will go to one side. So now we have a positive side and a negative side. One side is more negative. Now you might have the odd positive charge in here and the odd negative charge in here, but we have essentially one side of it as positive and one side of it as negative. This is called polarization, meaning you're putting the charges in different poles. If we were to just slice it right here on this line, we would end up having a positively charged pole and a negatively charged pole, right? That's what that means. That's what polarization is. It's when you separate charges. You separate charges. Now, the way you can charge something like that is by conduction or induction. We talked about conduction is when you touch. If these were to touch, induction is when they don't. We just gave you a demonstration here. See, they're not touching. This would be induction because they're not touching. If you charge it by conduction, what would end up happening is it's a slightly different process. Conduction would be, well, I guess I don't have to draw it. What would happen is, I guess I can. It'd take too long. Let's say you had two poles. One of them was positively charged. The other one was neutral. Okay? When you touch them, the charges separate out and they try to evenly distribute one another. Now, in that situation, if one's neutral and one's positively charged, most likely there won't be enough electrons to make both neutrally charged. So what will happen is the negative charges will leave the neutral, and some negative charge will leave the neutral and go into the positively charged rod, making both slightly positive, but less positive than that first rod was at the beginning. So that's charging by conduction and charging by induction. And that's polarization, when the charges separate and go into the different sections. Grounding. Grounding is an important term. I believe it's on page 548. Grounding. The book says, which is the process of connecting a body to earth to eliminate excess charge. So if you've ever seen in your house a copper wire that is just connected really to nothing, and in like a fixture, if you were ever seeing somebody replace a ceiling fixture, like a ceiling light, you'd see there's a copper wire that they do something interesting with. If you, like, let's say, like I'm looking at a fan right now, but if you were to replace a fixture, it's actually pretty easy. You'll see on the fixture itself, this is how to replace a light. Not that I recommend doing it, but get a professional to do it, but it's really not that hard. Make sure you turn the power off. but there are two wires coming out of the house. Um, one is usually red, one's usually black. The red one's usually the hot. You connect, and coming out of the device is usually like a red and a black as well. You connect the red to the red and twist it with one of those twisty tie thing, one of those. Uh, I can't think of the name of them right now because it's late. And then the black connects to the black with the wire nut, and then but there's a third one. Usually it's just a random copper wire, or it might be like a green wire with a little copper end to it. And what that connects to is one of two things. There might be a copper wire coming out of your house, or there might be a screw or something that connects to, that's connected to your house. What happens is if that fixture has some sort of charge goes through that, like through the red and the black, the hot, the red, if some charge, like let's say, lightning strikes or something, or there's some sort of excess charge that gets sent to your house, instead of going to that fixture and destroying that fixture, exploding that fixture, it will go through that fixture and just keep going in a loop until it gets to that charge, that ground wire, which is that green one or the copper one, and then it will go into your house, into like the wooden beams of your house and everything, and down into the earth. And that might be like, oh no, it's going into the structure of my house. It doesn't hurt it at all. What it does is it's dispersing it. If it didn't have a place to disperse, it would try to come out through that fixture, that light, and it would destroy the light, or it could, cause problems. Grounding electricity in Earth is fine because the Earth is so huge, it can take, excess charge of some kind. I mean, picture this: if you had, if you're a little child, let's say I'm having, Susanna help me carry something in, and she's carrying a brick. Let's say she's carrying a brick across my yard. She's struggling with this brick. If you hand her one more brick, that's going to be probably too much for her. Or if she has two, you hand her a third one, she's going to probably topple right over. Okay, adding even just a little bit more to her would make a huge difference. But let's say there's somebody really, really strong, like like Jason. Jason got those jacked arms, picking up 400 pounds, right? And he's got, like, let's say he's got 100 bricks in this container that he's carrying. He's carrying 100 bricks up, across the yard. And then somebody's like, oh, can I give you one more brick? I mean, if you're carrying 100 bricks, what difference does it make, right? Or even more, like if it was coins or something. Let's say you had a whole basket full of coins, right? If somebody has 3 more nickels and they throw it in there, it's not really going to make a difference, right? Same thing with the Earth. The Earth has so many charges that it's not going to make much of a difference. That's where we ground things, because the Earth can take it. It's so huge. Do I want to get into Coulomb's law yet? I'm not going to get into Coulomb's law yet. I will cover that next time, but I will talk about the units again. The units for charge, we call charge lowercase q. We give it the letter lowercase q. That's the letter we represent charge with in an equation. So if you saw something like, I don't know, q equals n times e or something, this q means charge. Okay, that's charge. You can't use a c because we're going to talk about c is something else in an equation. Now, this is where it gets confusing. The units are coulombs. Like you could have like 5 coulombs of charge. Okay, 5 coulombs. And you can abbreviate that C. Okay, 5 coulombs, 5C. Okay, what I'm talking about is the symbol for the unit, not the symbol in the equation. This is what people get confused sometimes. It's like when you have M. If I were to say, what is M? Well, it depends on what you're talking about. M could be mass if you're talking about an equation, like F equals M times A, or it could mean meters if you're talking about a unit, right? Just like that, C can be different things, okay? C, which we'll talk about at some other point, C talks about capacitance in an equation, but it's in the unit, it's coulombs, okay? Coulombs And coulombs is the unit for the unit of charge. And it's a base unit, so you couldn't say something like, what does coulombs mean? It is a base unit. Um, I believe if you wanted to be technical, it's like amplitude per second or something like that, but it doesn't break down like newtons breaks down into kilograms times meters per second squared. Coulombs is coulombs. It doesn't break down into anything. Oh, I'm frozen. I didn't even notice. Keep listening. Almost done. But to give you an idea, some real life applications. Coulombs are actually pretty big. One coulomb. Static electricity is about a couple of microcoulombs. A AA battery carries like 5,000 coulombs over its entire lifespan, but that's a long, long time. But a lightning bolt in an instant is like 15 coulombs. So you see, it's a fairly large thing, um, and and we'll talk a little bit more about it next time. I'm going to talk about Coulomb's law next time.